Hello everyone, welcome back to your Statistical Methods class. My name is Jessica Bray and I'll be the instructor for today's lecture. Before we get started on any new material, let's go ahead and review what we went through last time. In the last lecture, we learned about histograms, which are graphs that show how a variable is distributed in a group. Specifically, we learned about two types of histograms, frequency histograms and density histograms. In a frequency histogram, the height of the bar shows the frequency, so each bar shows the number of individuals per unit of the variable. Density histograms are a little bit different. In a density histogram, the height of each bar shows the density. So here, the height of each bar shows the percent of individuals per unit of the variable that had a certain value on the variable. And with density histograms, we can find the area of the bar. The area of the bar are the percent of individuals within a given interval. And to find the area, we multiply the height of the bar times the width of the bar. Let's look at an example of a density histogram. Here we have a density histogram that shows the distribution for ages of Titanic passengers, and the unit for age is 1 year. The height of each bar shows the percent of passengers per year for a particular age, and the area of each bar shows the percent of passengers who fell in each 10-year category. And finally, we learned that with density histograms, the total area of all bars is always 100%. In the last lecture, we also learned about the normal distribution, which is also sometimes called the normal curve. And we can think of the normal distribution as a kind of histogram. The normal distribution is a bell-shaped theoretical distribution that's high at the middle and lower at each side. The nice thing about the normal distribution is that many variables resemble the normal distribution. So let's look at this for an example. Here, the bars in this graph form a histogram for the IQ scores of 10-year-old children. The normal curve is shown as a black line that runs along the top of the histogram. As you can see, the normal curve is a close but not perfect fit to the histogram. Here, the red lines indicate the part of the graph that represents children with IQs of 100 or higher. The area of the colored part is 50%, indicating that 50% of children have IQs of 100 or higher. That area under the curve is equal to the percent of individuals in that interval. Now take a second to think about what the total area under the normal curve would be. And that's right, the total area under the curve is 100% or equal to 1. Okay, so let's go on with some new material. Before we move on with any new material, please take some time to jot down any questions you may have about what we covered last time. Today we'll be talking about several different topics. First, we'll talk about mean, median, and percentiles. Then we'll talk about the distance from the mean, and we'll finish off by talking about deviations. Make sure to jot down questions to ask during office hours. Let's start with the histogram. Is this a frequency histogram or a density histogram? And how do you know? Now, hopefully you jot this down, but this would be a frequency histogram because we're looking at the number of children. Here's another question. How wide is each bar? That is, how wide is the interval represented by each bar? If you said around 5 IQ points, you'd be correct. So each bar here is about 5 IQ points wide. Now, looking at this specific bar, what range of IQ scores is represented here? When I say the range, I mean what's the lowest and the highest IQ scores represented by the bar. So specifically for this bar, the lowest IQ score would be represented by around 95 points, and the highest IQ score represented by this bar would be around 100. So the range for this bar would be from 95 to 100. All the children represented by this bar had IQ scores between 95 and 100. How about the height? What would be the height of this bar? The height of this bar is about 90. And how many children had IQ scores within this range of 95 and 100? Now we can roughly estimate this and say around 450. We know the bar is 5 units wide and 90 units tall, so 5 times 90 is 450. Here we can't tell exactly how many children had IQs in this range, but we can make an estimate or an educated guess. And we said that guess was around 450. So roughly speaking, what is the average IQ for all children in this whole histogram? The average IQ would be somewhere here in the middle where we can see it's probably 100 or close to 100 IQ points. The bar here with the 450 children is very close to the middle. Now this interval is for IQs between 115 and 120. What is a good estimate for the height of this bar? Yeah, I would say that a good estimate for the height of this bar might be around 50. And how many children had IQs in this range? We can take our estimate of 50, multiply it by the width of the interval, 5, and get an estimate of around 250. This is the interval for IQs between 125 and 130. What is the approximate height of this bar highlighted here? This bar is around maybe 20 high. So we can use this estimation of 20 to estimate how many children are in this range. We get that 20, multiply it by width of 5, and get around 100 children within this IQ range. Now here's another question. What happens to the height of the bars as they go further from the average of 100? And we can see that the height of the bars does seem to decrease as they go further away from that score of 100. Now here's another question. Where do IQs of most children fall? Would you say they fall close to that average score or far away from the average? Looking at the histogram here, we can see that most children's IQ scores are close to that score of 100. Now when children fall close to the average, like the children in the IQ range of 95 to 100, we say that they deviate only a little bit from the average. But when children fall further away from the average, we say they deviate a lot. The deviation is the amount the child differs from the average. Most children deviate only a little bit from the average, but a few out here on the graph are very short or very tall, so they deviate a lot from the average. Later today, we'll be returning to this idea of deviation, and it's a really important idea within statistics. But for now, we're going to talk a little bit more about the average. In statistics, the average is called the mean. In this class, sometimes we'll use the word mean and sometimes we'll use the word average, but both words mean the same thing. One time, I might say the average height of men is 5 foot 10 inches, and later I might say the mean height of men is 5 foot 10 inches. Either way, we're essentially saying the same thing. We also say that the mean is a measure of central tendency. That is, if we measured a sample of individuals on some characteristic, like height, weight, or IQ, it's helpful to have a number that tells us what is the typical or central or middle score for the sample. For instance, in this graph, earlier we said that the center or middle for IQ scores in the sample is about 100, but that's just an estimate. Sometimes we need to be more precise about what we mean by the center or middle, and that's what the mean is useful for. I'm sure you already know how to calculate the mean, though probably you were told it was called an average. So we're not going to go over the calculations in great detail, but to calculate the mean or average, you add together all the scores for all individuals, then divide by the number of individuals. So here in the example, we have 5 scores, 2, 4, 5, 6, and 8. We're going to add all those up and divide by 5 to find the mean. Statisticians use special symbols and abbreviations when writing mathematical formulas. These special symbols and abbreviations are called mathematical notation. We're going to see how the mean is written in mathematical notation. During the first lecture, we already learned a little bit about mathematical notation. We said that if a variable is represented by the capital letter X, then the values of the individual on X are written using lowercase letters. So x1 is the symbol for the value of individual 1 on variable X, x2 is the symbol for the value of individual 2 on variable X, and so on. Just as a quick refresher, what do we call the little number that tells us which individual is being referred to? So here, what do we call the numbers 1, 2, or 3? Those numbers are called subscripts. This is the example we looked at earlier that shows how to calculate the mean. In this example, 2 is x1, 4 is x2, 5 is x3, so on and so on. This is the next mathematical symbol we'll use. This is sigma. Sigma is a Greek letter. It's a capital letter S. Greek letters are often used as symbols in mathematical notation. In mathematical notation, sigma means the sum of. This is a sigma followed by a lowercase x. It means the sum of the values of x. In this example, sigma x is the symbol for the sum of the values of x. That is, sigma x is the symbol for 2 plus 4 plus 5 plus 6 plus 8. The next mathematical symbol is n, the capital letter N. N means the number of individuals in a group or sample. So in our example here, n would be equal to 5. And as we said before, sigma x is the symbol for 2 plus 4 plus 5 plus 6 plus 8. So if we write sigma x divided by n, that means the same thing as the formula listed here. Using the mathematical notation allows us to write the formula very quickly. We just need to learn one more symbol for now. This symbol is x with a little bar on top of it, sometimes called x bar. X bar is the symbol for the mean of the variable x. That little bar on top of the x means the mean of. So in our example, we can write the formula x bar equals sigma x divided by n. Most of the time, we will read it like this. The mean of x is equal to the sum of the values of x divided by n. So this is the formula for the mean using mathematical notations. Now, as I said earlier, the mean is sometimes called a measure of central tendency because it gives us an idea of the central, typical, or middle value of a distribution. Next, we're going to talk about the median, which is another important measure of central tendency. The median is the score at the 50th percentile in a sample of scores. But you might be asking, what is a percentile? So we're going to go through a few examples to hopefully make this clear. The first example is that at the score of a 10th percentile. A score is at the 10th percentile if it is equal to or higher than 10% of all scores. This arrow is pointing at the children with an IQ of 81. These children are at the 10th percentile because they scored equal to or higher than 10% of all other children. If we look at the bars of the histogram to the left of an IQ of 81, the area of these bars is about 10%. So we know that 10% of children have an IQ equal or less than 81. Thus, all the bars to the left of 81 represent those 10% of children. Now let me ask you another question. What percent of children had an IQ higher than 81? 90% of children had an IQ higher than 81. We can estimate or calculate this because we know 10% of children have an IQ equal to or lower than 81. So the other 90% must have an IQ higher than 81. That means that the area of all the bars above that score of 81 is also 90%. Let's go through a couple more examples of percentiles. A score that is at the 75th percentile is equal to or higher than 75% of all scores. So here, what IQ score is at the 75th percentile for the histogram? That IQ score would be around 110. So that means that 75% of children had IQ scores equal to or less than 110. And what percentage of children had IQ scores higher than 110? Around 25% of children had IQ scores higher than 110. Let's go through this next example. A score at the 90th percentile is equal to or higher than 90% of all scores. So here, if we look at the histogram, an IQ of 119 is at the 90th percentile. That means that the area to the left of this dot here would be 90% of our total sample. That also means that around 10% of children had an IQ score higher than 119. So now that you understand what a percentile is, you can understand what the median is. The median is the score at the 50th percentile. So the median is equal to or higher than 50% of all scores. Therefore, it is also lower than 50% of scores. So the median is right in the center of the distribution of scores. That's why it's a measure of central tendency. There are two main measures of central tendency, the mean and the median. Now that you know about these two measures, you might be asking, which one is better? Now the answer is that they're both useful in different ways, and in this course we're going to be using them both. And we'll also be using percentiles a lot too. If you have two measures of central tendency, they will sometimes agree with each other, but not always. When they both agree, the mean is equal to the median, but sometimes they disagree. Sometimes the mean may be greater than the median, and sometimes the mean may be less than the median. It all depends on whether the distribution of scores is symmetric, positively skewed, or negatively skewed, and we'll go through these in more detail. First, if a distribution of scores is symmetric, the mean and median are always equal to each other. A symmetric distribution is a distribution in which the left side and the right side look very similar, except that they are mirror images of each other. So this is a normal distribution and it's symmetric. If we were to fold along that IQ score of 100 and put the left side on top of the right side, they would be very close to each other. This is one indication that the distribution is symmetric. The distribution in this histogram is almost perfectly symmetric, and so we expect the mean and the median both to be the same. In this histogram, the mean and median are both 100. In all symmetric distributions, the mean and median are equal to each other. Next, let's talk about positively skewed distributions. If a distribution is positively skewed, the mean is greater than the median. A distribution is positively skewed if it's shaped like this. Most individuals are on the left side of the histogram, so there's a big hump there. But there are also a few individuals way off to the right side of the histogram, forming a long tail. In a positively skewed distribution, the tail points to the right. That is, the tail points in the positive direction. When I say it points in the positive direction, I mean that the x-axis is like a number line, where positive numbers are to the right of negative numbers. Here's another positively skewed histogram. It shows the fares paid by the passengers on the Titanic. This histogram has a hump on the left side. The tall bars here on the left indicate that most passengers on the Titanic paid less than $50, but there's also a long tail to the right. And we can see that some passengers paid more than $100 or even more than $200. Remember, this was in 1912 when $200 was a lot more money than it is now. The 10th percentile for fares on the Titanic was $7.55. So that means that 10% of passengers paid less than $7.55. They probably slept in the hold of the ship. The 50th percentile, the median, was $14.45. So half of the passengers paid less than $14.45. The other half paid more than $14.45. Here's the 75th percentile, $31.20. Here's the 90th percentile at $77.62. At the 95th percentile, we have $120. So 95% of passengers paid less than $120. But there were 5% who still paid more than that. And here, way out at the tip of the tail, are a few passengers who paid $200 or more. We sometimes call these extreme values outliers. And here's the mean and the median. As you can see, the mean fare was greater than the median fare. This always happens with positively skewed distributions. When you average in the few passengers who paid more than $200, the mean gets pulled to the right, but the median isn't affected by those high scores. So to sum up, in a positively skewed distribution, the tails point to the positive direction, that is to the right, and the mean is pulled to the right of the median towards the tail. Finally, we come to negatively skewed distributions. A negatively skewed distribution is just the opposite of a positively skewed distribution. In a negatively skewed distribution, the mean is less than the median. A negatively skewed distribution is one where the tail points to the left in the negative direction. Here's another negatively skewed histogram. It shows reaction times of participants in a psychology experiment where the participants had to hit a button when they saw a word. As you can see, the hump is on the right. Most participants took between 60 and 80 seconds to hit the button. There's a tail pointing to the left. A few people had reaction times of 30 or 40 milliseconds. You can see that one or two even reacted more quickly than that in 20 milliseconds. Alright, so here's a question for anybody that knows about these types of experiments. Why are there a few people out here who reacted in only 20 milliseconds? Well, nobody reacts that quickly, typically. These people at 20 milliseconds jump the gun without waiting for the word to appear, kind of like someone in a race who takes off from the starting line before the pistol is fired. So this shows the median and mean. The median was 72 milliseconds. Half the people had reaction times more than 72 milliseconds, and half had reaction times less than 72. But the mean is lower than the median. When you average in these extremely short reaction times, 20 and 30 milliseconds, the mean gets pulled to the left. So to sum it up, negatively skewed distributions work the opposite way from positively skewed distributions. In a negatively skewed distribution, the tail points in the negative direction, that is towards the left, and the mean is pulled to the left of the median towards the tail. So in both positively skewed distributions and negatively skewed distributions, the mean gets pulled toward the tail and away from the median. In positively skewed distribution, the tail points to the right and the mean gets pulled to the right. In negatively skewed distributions, the tail points to the left and the mean gets pulled to the left. Okay, now we're about to move to a completely different topic, distance from the mean. Let me show you what's meant by a score's distance from the mean. Here's the distribution of IQ scores that we've been using in this lecture. The mean of the distribution is around 100. Let's say that a child has an IQ of 110 marked by this green dot. The child's IQ is 10 points away from the mean. That is, if you measured from the mean, which is 100, to the child's IQ score of 110, the distance between these 2 points is 10 units. We say that the distance from the mean for this child's IQ is 10. Here's the formula for the distance from the mean. We subtract 100 from 110. That is, we subtract the mean from the child's score. Let's try it again with another child. This child has an IQ of 130. This child's IQ score is 30 points or 30 units away from the mean. So the distance from the mean for this child's IQ score is 30. Here's the formula. The distance from the mean is 130 minus 100, which is equal to 30. Again, we're subtracting the mean from the child's IQ score. Let's go through another example. This child has an IQ score of 90. This child's distance from the mean is 10. In other words, if we measured between 90 and 100, the distance is 10 units. Here's the formula. 100 minus 90 is 10. The distance from the mean is always positive with one exception, and I'll mention it in a minute. Here's another example, a child with an IQ score of 70. So take a minute to jot down what the distance from the mean would be for this child. The distance from the mean here is 30. Remember that the distance from the mean is always positive except for one exception that I'll get to in a second. Here's a child whose IQ is 100. What is their distance from the mean? This child's distance from the mean is 0. That is, if we subtract 100 from 100, we get 0. There is 0 distance between this child's score and the mean. This is the exception that I've been mentioning. If a score is equal to the mean, then the distance from the mean is 0. So for all other scores, the distance is positive. But when a score is equal to the mean, the distance is 0. So let me repeat. A score's distance from the mean is always positive or 0. Distances are never negative. So to calculate a score's distance from the mean, we either subtract the mean from the score, or we do the opposite and subtract the score from the mean, whichever gives a positive number. If we do the subtraction and get a negative number, we know we've made a mistake. Now we're ready to go on to the next topic, which is deviations. The deviation is the same as the distance from the mean, except a deviation is positive if the original score is above the mean, and is negative if the original score is below the mean. Let me explain what I mean here. Here's the same distribution of IQ scores that we've been using, where the mean IQ is 100. And here's a child whose IQ is 110. Now, if the score is 110, we know that the distance from the mean is 10. And the deviation here is also 10. The deviation and the distance from the mean are exactly the same. The formula for the deviation is 110 minus 100. That is, the deviation is equal to the child's original score minus the mean. Now let's try it with a child whose IQ score is 90. What is the distance from the mean for this score? The distance from the mean is 10. But here's something really important. The deviation is not 10. The deviation is actually negative 10. Here's the reason. When the deviation is less than the mean, the deviation is always negative. In this example, the child's score is 90 and the mean is 100. The child's score is less than the mean and therefore the deviation must be negative. The distance from the mean is 10 and the deviation is negative 10. Here's the formula for the deviation. 90 minus 100. That is, the deviation is equal to the child's original score minus the mean. So let's try it again with a child who has an IQ of 130. The distance from the mean is 30. The deviation is also 30. The original score is 130. Because 130 is above the mean, the deviation is positive and equal to the distance from the mean. Now let's look at this child who had an IQ score of 70. Their distance from the mean is 30. And what is the deviation here? So take a few minutes to jot down what that deviation would be. The deviation is negative 30 because 70 is less than the mean. So let's do this one more time. Suppose a child's IQ score is at 100. What is their deviation? Right, the deviation is 0. If the original score is equal to the mean, then the distance from the mean and the deviation are both 0. So now we can understand how the deviation is the same as the distance from the mean, except a deviation is positive if the original score is above the mean, and a deviation is negative if the original score is below the mean. So a deviation can be positive, negative, or 0. Specifically, if the original score is above the mean, the deviation is positive. If the original score is below the mean, the deviation is negative. And if the original score is equal to the mean, the deviation is 0. A deviation indicates how far a score is from the mean. That is, as soon as we see the deviation, we know the distance from the mean. And the deviation indicates whether a score is above or below the mean, because depending on whether the deviation is positive or negative, that tells us whether the original score was above or below the mean. The formula for deviation is super simple. We just subtract the mean from the original score. Let's take a moment to practice calculating deviations. Here we have a data table that shows IQ scores for 5 children: Sam, Crystal, Eddie, Claudia, and Diego, with the mean of these 5 IQ scores being 100. Just to make things easier, we'll write in the mean next to each child's IQ score. Now, take a minute to calculate the deviation for each child. Here's the formula to help you. Take the score and subtract the mean from the score. Here are the deviations. Now, if we look at Sam, he has a score of 150. 150 minus the mean of 100 gives us a deviation of 50. Diego had a deviation of minus 50. If we look at Diego's original score, he had a score of 50. 50 minus the mean of 100 gives us minus 50. So today we've discussed several topics. First, we discussed two measures of central tendency, the mean and the median. Both represent the center or middle of a distribution. We also discussed percentiles, and we discussed distributions that are symmetric, positively skewed, or negatively skewed. We explained that the mean and median are the same in symmetric distributions, but in positively skewed and negatively skewed distributions, the mean gets pulled away from the median towards the tail. Finally, we discussed distance from the mean and deviations. Okay, now let's go through a presentation on statistics at work. Last time we looked at the relationship of gender to survival on the Titanic. Today we're going to be looking at the speed of horses in the Kentucky Derby. Here's a research question. Has the speed of winners in the Kentucky Derby changed over the years? In order to answer this research question, step 1 is to identify the variables whose relationship is being examined. Here, what do you think those variables are? There are two variables involved: the speed of the winning horse and the measure of when the race occurred. In this case, we'll be using the race in which the race occurred. To analyze the data, I entered information about the Kentucky Derby in an Excel sheet. Each line of the Excel sheet represents a different horse. For each horse, there are 3 variables. The first variable is the horse's name. The second line is the year when the horse won. The third variable is the horse's speed. So on the first line, we see that Ben Brush was the winner in 1896, and the speed was 51.66 seconds. The second line is for a horse called Typhoon 2, who won in 1987. The speed was 49.81 seconds. And so it continues on each line with a different horse and the 3 variables we recorded: name, year, and speed. The last horse in the Excel file won in the year 2000. So we have data for more than 100 years. The second step is to identify the descriptive statistic that will be used to examine the relationship between speed of the winner and the year the race was run. We have one continuous variable, the speed of the winner, and we have one discrete variable, the year of the race. The descriptive statistic we can use to describe the relationship between a continuous variable and discrete variable is the correlation. We will learn a lot more about correlations later in the course, but right now you can trust my calculations are correct. Step 3 is to make a prediction about what we'll find. What do you predict? Do you predict that the speed of the winning horse has increased over the past 100 years, decreased, or stayed the same? Take a second to jot down your prediction. Up here is the crucial number. The correlation between the year of the race and the speed of the winning horse was 0.749. As you'll learn later in the class, a correlation of 0.749 indicates a pretty strong relationship. Step 4 is to select a graph that's appropriate to display the findings. To show the relationship between a continuous variable and a discrete variable, we can use a scatter plot. Here's a scatter plot. It's a clever way to show the relationship between two variables. Along the x-axis is the year the race occurred. Along the y-axis is the speed. So if we go to the year 1896 on the x-axis and go straight up, we can see that the speed was a little bit less than 52. That's the horse on the first line of the Excel sheet I showed you. We can do the same thing for the horse who won in 1897. We can trace straight up from 1897 and find that the speed of this horse was slightly less than 50. This was the horse on the second line of the Excel sheet. So each dot in the scatter plot represents a different horse. And here we see the horses continuing up to the year 2000. Now what would you approximate the speed of the winning horse in 2000 to be? Right, so the speed of this winning horse would be around 54 or 55. Now what about our research question? Has the speed of Derby winners changed over time? How has this changed? Well, we can see that over these 100 years, the speed has seemed to increase. Here's a straight line I've drawn through the dots. It's called the regression line, and you'll be learning about the regression line later in the course. Its usefulness is that it shows in a simple way how the horse's speed has changed over time. It's also possible to draw another line through the dots that's not straight. This is called the lowest line, and it's not straight. As you can see, it tells a slightly different story than the straight regression line. The lowest line is curved, and it seems to indicate that yes, the speed of winners increased between 1896 and 1960, but after 1960, the speeds didn't increase or decrease. To finish up our research question, we need an inferential statistic. The purpose of the inferential statistic is to determine whether findings could have occurred by chance. As it happens, when we're looking at the relationship between two continuous variables, the correlation is an inferential statistic. As you may recall, the correlation is also a descriptive statistic that we used. And here it is again. The correlation was 0.749. So now we're coming to the last step, step 6. We're going to check if the p-value to see if the probability is low that the findings occurred by chance. We say p-value, and that's short for probability value. Here marked in green is the probability that the findings occurred by chance. The printout says the probability is 0.000. Now that's very low, and that's important and interesting. We found that the correlation between the year of the race and the speed of the winning horse was 0.749. This probability of 0.000 tells us the probability was very low that this correlation occurred by chance. So there's really something going on with the relationship between year and speed. So to review, there were 6 steps we went through to evaluate our research question. First, we identified 2 variables, speed of the winning horse and the year the race was run. Second, we identified the correlation as the descriptive statistic we should use to look at the relationship between these two variables. Third, we made a prediction about what we would find. Fourth, we graphed the data using a scatter plot because a scatter plot allows us to see relationships between two continuous variables. Fifth, we calculated the inferential statistic. In this case, the inferential statistic was the same as the descriptive statistic, the correlation, and we found a large correlation between speed and the year of the race. Sixth, we looked at the p-value to see if what we found could have occurred by chance. The probability of the large correlation occurring by chance was very low, so that told us there was really some relationship between the year the race occurred and the speed of the winner. Alright everyone, that's it for this lecture. Please make sure to jot down any questions you may have over this material and bring it to office hours for discussion.